demonstrate the techniques perfectly. Now, in our first example, we have a situation where a lady called Patricia and borrows €20,000 to buy a car over a period of 4 years. She pays off this loan in 48 equal payments. The first one is to be made 1 month after she signs the agreement. Now, it's very, very important that we highlight that part there, because this is actually the only situation in which it's comfortable for us to use the amortisation formula. Okay, if time has been measured in months, the payments must commence 1 month after the signing of the agreement for the amortisation formula to actually work. Now, to begin with, we're going to do our usual process of calculating 1 plus little r. Remember, little r is the decimalised interest rate. Now, 1 plus little r, 1 plus the decimalised monthly interest rate, is going to be equal to 1 plus the annualised interest rate, 6.8% divided by 100. So you divide 6.8 by 100, you get 0.068, and then you add 1, which gives you 1.068. Now that is annualised, so what we do is we put that to the power of 1 over 12, because there are clearly 12 months in the year. Okay? Now, when we do that calculation, we obtain that 1 plus little r is equal to 1.005497,367. So 1 plus little r is equal to that value. Now that obviously means that small r, we subtract 1 from that, and that's going to give us 0.05497,367. So there you go. We have our first two components in line. We have small r and we have 1 plus r. Now small r, as you can see, is mentioned here. And then capital R, or 1 plus small r, is mentioned here, and again here. So now all we have to do is substitute into our formula. And the final component here is P, which is the present value of our loan at the beginning of the agreement. So P in this situation is €20,000. So P equals €20,000. Now capital A, as always, is the future value. And this is the value of each payment on the day that Patricia actually makes the payment. So that's our monthly payment, capital A. So let's work this out. So capital A equals P, first of all, 20,000, multiplied by small r. Now we can see very clearly that small r is 0.005497367, multiplied by 1 plus little r to the power of n. That's 1.005497367 to the power of the amount of payments that this woman is actually going to make. Now Patricia is going to pay this car off in 84 equal payments. So that's to the, in 48. So that's to the power of 48, excuse me. Now that's all to be divided by 1 plus little r, again highlighted in red, 1.005497367 to the power of 48, and then subtract 1. Now the beauty of the amortisation formula is that we merely have to do this calculation and then we are done. Okay, so it's a fantastic way to approach the question, as long as that you're absolutely sure that it works. Okay, now when we do this calculation, we obtain a monthly repayments of €475.19 per month. Okay, now as I said, the amortisation formula is a fantastic formula to use as long as you know you're allowed to use it. Now here's the problem. The problem with the amortisation formula is that the payments must begin 1 month after signing the agreement. That's assuming that we're measuring time in months. Secondly, the payments have to continue on in the normal way in monthly payments until we finish paying the loan, whatever number of months later. It doesn't allow for any balloon payments or any final balancing payments like PCP finance. So we have to be very, very careful that we are allowed to use this formula before we actually do. And that's why, to be honest, I would recommend that you do this question the next way that I'm going to do it, as opposed to this way. Having said that, the amortization formula works brilliantly in this scenario. But remember, you must start paying off the loan 1 month after you sign the agreement, and you must finish the loan with a zero balance in the normal way, with all of the payments being equal. If there's any alteration to the size of the payments, the amortization formula cannot work. Okay? Now, to introduce the next method before we do it, it's based on a very, very simple fact. The present value of the loan on the day of signing the agreement, we're going to express it as a geometric series, where P1 is the present value of the first payment, where P2 is the present value of the second payment, all the way up until the loan finishes off when we work out the present value of the 48th payment. Now, that's actually a better way to do this. You're less likely to make errors, as you'll see in the following two questions. So the initial value of the loan is equal to the sum of the present values of all of the future payments made against the loan. So P1, P2, P3 and P4, all the way up to P48, are the present values of each of the payments that are made against the loan. Okay? Now we're going to use that technique to do the question again. So method 2, expressing the payments as a geometric series. Now we're going to, first of all, we're going to say that 1 plus little r, we'll save ourselves the hassle of working that out again. It's 1.005497367. Now 1 plus little r is calculated the exact same way as we did previously in method 1. Okay? In this method, we use this fact. The present value equals the payment divided by 1 plus r to the power of n, to the power of the amount of time which has passed. Now, the simplest way that you can possibly figure this one out is that when, as we said in the first video, if you feel that the value of a fund should be going up, you multiply by 1 plus r to the power of little n. And that's why in video number 1 for savings accounts, we multiplied by 1 plus little r to the power of n. However, in a loan account, we know that the value should be going down. So in this situation, you should be dividing. So remember, if you multiply things, the value goes up. If you divide things, the value goes down. Okay? So the initial value of the loan is equal to the sum of the present values of all future payments made against the loan. And as I said, that's going to be our technique for this question. Now, the initial value of the loan is €20,000. So that was the initial amount of money that was borrowed by this lady, Patricia. Now, we don't know what our monthly payments are yet, so we're going to call it A. Now, I need to divide by 1.005497367 to the power of the amount of time that has passed since signing. Now, this is Patricia's first payment. And the first payment is made 1 month after signing, so this should be to the power of 1. Her next payment is going to be made 2 months after she signs the agreement, so this should be A divided by 1.005497367 to the power of 2, because at this stage 2 months have passed before she makes that payment. And this continues on until she makes her final payment. So that's plus A divided by 1.005497367 to the power of the amount of time which has passed. Now her final payment is made 48 months after signing. Because remember, the first payment is 1 month, so it's payment number 1, 2, 3, 4, 5, all the way up to 48. So that is to the power of 48, because it's 48 months after she signs the agreement, or alternatively 4 years. Now, A little bit like what we did in the savings account question, what I'm now going to do is I'm going to notice that we have an A everywhere. We have an A there, an A there, an A there. Every single one of those A's is the same. So I'm going to take out that common A. So on the next line, 20,000 is equal to A into 1 over 1.005497367 to the power of 1 plus 1 over 1.005497367 squared plus all the way up to the last payment, which is 1 over the same number, 1.005497367 to the power of 48. Okay? Now, I don't like fractions. To be honest with you, I would often skip the line that I've just written down and go directly into decimals. But because I don't like fractions, I'm now going to calculate what is 1 divided by 1.005497367. So we grab our calculator and we work out what that is. And it makes our question much, much simpler, as in the following step. So 20,000 equals A into 1 divided by that number is 0.99453268887. So this number here is equal to this number here. So all I've done is I've now put that to the power of 1. The next term in the series is the same number, 0.9945326887 squared, plus ... all the way up to the last one, which is 0.9945326887 to the power of 48. Okay, so that's including all of the terms of the series. Now that division I've done is purely and simply to avoid fractions. And then I would put that 0.99 etc. number into the memory of my calculator to make the steps easier in the next few minutes. So then we have 20,000 equals, I hope you can see that here we have a geometric series. Okay, this part that I'm highlighting is a geometric series. The power starts at 1, then 2, and goes up to 48. So it's a geometric series with 48 terms. Now I think you can see that every time we move from one term to the next, we're adding in one additional 0.99453268887. So the first term and the common ratio are calculated as follows. The first term, A, is equal to 453268887, and that's also the number that we're multiplying every time. So that's our common ratio, capital R. Now, as I said in the first video, it's very, very important that you just have a brief look at the common ratio. Okay, the common ratio in this case is smaller than 1. Now, that is what we would expect because this is a loan. Okay, we feel that the value of a loan should be decreasing. And remember, decreasing made me divide at the start of the question. It also makes me check whether the common ratio is bigger or smaller than 1. Now, because the common ratio is smaller than 1, this loan is going to go down, and we all want to eventually pay off our loans. So that's good news for us. So we now work out S48 of our geometric series. So the sum of the 48 terms of this series. Now in the log tables, we look up the formula. Sn equals A multiplied by 1 minus r to the power of n over 1 minus r. And remember, that's the version we use when r is smaller than 1. Remember, if capital R was bigger than 1, we would reverse the sign on the top and on the bottom, and we would have A multiplied by r to the power of n minus 1 divided by r minus 1. Okay, so which version we use depends on the value of R. So for savings accounts, capital R should be bigger than 1. For loans and mortgages, it should be smaller than 1. Now, all that's left for us to do is to put these numbers into our formula. So 20,000 is equal to A multiplied by small a, which is 0.99453 26887, multiplied by 1 minus the same number, 0.994536887, to the power of 48. Now that's because there are 48 terms in the series, okay? And then that all has to be divided by 1 minus r. So 1 minus, here we go again, 0.99453 26887. Okay? So all we've done there is we put in our value of capital R and our value of small a into the series. The next job that we have to do is this part here that I'm highlighting in blue. We now grab our calculator and we work that out. Okay, so we work that part out with our calculator and we obtain that 20,000 equals A multiplied by 42.088174446. Okay, now the last step of the question, we have to do the opposite to multiplying by that number, 42.088174446, which is to divide by it. So the monthly payments are equal to 20,000 divided by that long decimal number, 42.088174446. And clearly it gives the exact same number as we had before, which is €475.19. Now, I think that you would all agree that in this particular situation, the amortization formula arrived at the answer much more quickly than using the geometric series. If we compare the two techniques, you can just see the difference in the level of effort. The amortization formula, extremely short, and then the sum of the geometric series, you can see it's that little bit longer. Now, the thing is, the amortization formula can only be used in certain conditions. And remember, those conditions are the loan repayments must start 1 month after the signing of the agreement, and they must finish in the normal way with a balance of 0 after n equal payments. If there are any changes during the life of the loan, well, then the amortization formula becomes a problem. Okay, so it's important that you know both techniques, but it is vitally important that you know when you can and when you can't use the amortization formula. If you're very confident with it, by all means use the amortization formula, but if you're in any way unsure, you're possibly as well off actually using the geometric series formula. Now, in the final question in this video, the amortization formula is destined to let you down. Okay, so this is the kind of situation that we need to guard against and understand that we can't blindly trust the amortization formula. So our question here reads, Marie borrows €50,000 to start a new business. She agrees to pay the bank back the loan over a period of 6 years. Okay, so the period is a little bit longer, at an APR of 5.6%. Now here's the difference. The bank agrees that Marie should start paying the loan on the first anniversary of signing the agreement. Okay, in other words, 1 year after she signs the agreement. So the bank are basically saying to Marie, Marie, we're going to give you that money. We know that at the moment you're setting up a new business, so you don't have any customers. So that means you're not going to have any money coming in. So we're going to give you a 12-month period where you can set up the business, not worry about paying us back. Your first payment is starting a year from today, and then you will start paying off on a monthly basis until you clear your loan on the 6th anniversary. So this loan is much more complex, and because it doesn't start a month after signing the agreement, we actually can't use the amortization formula. We can kind of make it work in a very weird roundabout way, but it's much easier to take this question as a geometric series. So remember the rule. The initial value of the loan must equal the sum of the present values of all future payments made against that loan. But before we start, our first port of call is to work out what the common ratio is. So 1 plus little r is going to be 1.056. So we take the 5.6%, we divide it by 100, and then we add 1. 5.6 divided by 100 is 0.056, and then add 1, that gives us 1.056. Now that's an annual interest rate, so we now have to put that to the power of 1 over 12 to convert it to a monthly interest rate. Now that's going to give us a value of 1 plus r is equal to 1.004551007. So that's 1 plus little r being the decimalized interest rate, the interest rate divided by 100. Remember, r equals 5.6 divided by 100, which is 0.056, and then 1 plus little r is clearly going to be 1.056. Now, remember the rule. The initial value of the loan, 50,000, must equal the sum of the present values of all future payments made against that loan. Now, it's a loan, so I'm expecting the value to be decreasing. And because I'm expecting it to be decreasing, I feel that I should be dividing by 1 plus r to the power of the amount of time that has passed. Remember, for savings accounts, funds go up, so you multiply. For loans, funds go down, so you divide. Now, let's imagine that the monthly payments are of value A, capital A. Her first payment, remember, her first payment A, and these are all equal payments A, is made 1 year after she signs. So the present value of that is going to be A divided by 1.004551007 to the power of the amount of time which has passed. Now 12 months have passed. She doesn't make this payment until 12 months after she signs the agreement. So the first payment is the power of 12 plus A over, well, her next payment, she's making these payments monthly, so it's going to be a month after that. So that's 1.004551007 to the power of 13, because another month has passed, plus ... all the way up to the last of these payments, which is going to be made on the 6th anniversary of signing the agreement. So that's 1.004551007 to the power of the amount of time that has passed. Now 6 years is 72 months, 6 multiplied by 12. So that final payment is to the power of 72. Okay? Now what we're going to do in the next step is exactly as in the previous question. So we just take out that common A. So 50,000, again, just to be clear about that, we have an A here, here, here. All of the payments have a capital A on top. So we take out that common capital A. So that's equal to capital A into 1 over 1.004551007 to the power of 12 plus 1 over 1.004551007 to the power of 13, and then the sequence continues until it reaches the last term, which is 1 over 1.004551007 to the power of 72. Okay, so this continues off for the life of the loan. Now, just as in the last question, I'm not really too fond of fractions. So the next thing I'm going to do to make my life a little bit easier, let's go red, is I'm going to work out what 1 divided by 1.004551007 is equal to, and that's going to be 0.995469112. It's just so much easier if I replace my fractions with that number. So all I've done to calculate that number is just go 1 divided by 1.004551007. Now, if I make that alteration, here's what I end up with. On my next line, I have 50,000 is equal to A multiplied by 0.995469112 to the power of 12. Because remember, over here we had the fraction to the power of 12. So my new decimal is to the power of 12 as well. And then that's plus 0.995469112 to the power of 13, plus all the way to the end of the series when I reach 0.995469112 to the power of 72. Okay? Now, clearly in the curly brackets again, just like in the previous question, we can see we have ourselves a geometric series. Okay? In this geometric series, the first term is 0.995469112 to the power of 12. And you can see very clearly that each time we move on to the next term in the sequence, we multiply by another 0.995469112. So the first term, A, is equal to 0.995469112 to the power of 12. And the common ratio is again 0.995469112. Obviously, if the first item in the series, the first term in the series is to the power of 12 and the second term is to the power of 13, that clearly means we must be multiplying by 0.995469112 each time. Now again in this case, the formula is going to be Sn equals A into 1 minus r to the power of n divided by 1 minus r. Clearly I'm using the r smaller than 1 formula. And I'm very, very happy that r is smaller than 1 because this is a loan and we want it to decrease in value. If the common ratio was bigger than 1, it would increase in value and then we would have a problem. We would effectively never pay off the loan. So on our next line, we now go back to basics and we say 50,000 is equal to A multiplied by the sum of a given number of terms. Now, be very careful here. If we had term 1 and then term 2 and then all the way up to term 12 and then term 13 all the way up to 72, we would have 72 terms. That's if we started at 1 and continued up to 72. But let's be clear here. The terms numbered 1 up to 11, there are no powers from 1 up to 11. Okay, my apologies. Just trying to wipe that out. There are no terms from 1 up to 11. So we need to remove those first 11 terms from our 72. Now this is a part where people always become confused. If we were counting from 1 up to 72, there will be 72 terms. But clearly from 1 up to 11 is missing. So 72 minus 11 is 61. Okay, so there are 61 terms in this series. Now, a lot of people would accidentally make the mistake of putting down 60, that they would take 1 year away from 72 and they would say 60, but you're actually taking 11 payments away. Now, that means that 50,000 equals capital A multiplied by small a, which is 0.995469112 to the power of 12. Remember, capital A has, small a has a power of 12 in it. Then that's multiplied by 1 minus r to the power of n. So that's 0.995469112 to the power of 61. Divided by 1 minus 0.995469112 9112, 1 minus capital R. Now, as in the previous question, the next thing that we do is we calculate what all of this, everything except A on the right-hand side, is equal to. But the big thing that we have to be very careful about there is that unusually in this question, there's a power here in small a, because this woman, Marie, has been given a 12-month rest before she starts paying back the loan. Now, this is actually a question that the examiner hasn't asked yet, but it's a very, very practical question in financial circles where you give businesses breathing space before they begin to pay back their loan. And this woman has been given a 12-month breathing space. So just be very careful that this can only be done with the geometric series. Okay, will only be done comfortably with the geometric series approach. Now, once we do that calculation, we have 50,000 is equal to capital A multiplied by 50.5700211. And then the final line is clearly just to divide across by that number. So the monthly payments that Marie will have to make once she begins repaying the loan is 50,000 divided by 50.57, etc., etc. And that's going to work out at €988.73 per month. Now, I would advise you to have a long, close look at the question that I've just done, because it is one of those things that the examiner hasn't asked yet. Okay, simple situations where you use the amortisation formula, or the middle question where you can approach it using a geometric series, they've appeared. But just watch this one. Okay, it's a little bit different. So remember, you can only use the amortisation formula as we did in the first question when the loan repayments begin 1 month after you sign the agreement and end in the normal way, having had a set of equal repayments. Guys, thanks a million for watching. In the next video, we're going to look at pension funds. Thanks again for watching. Talk to you soon. Bye-bye now.